to celebrate the achievement of two people, Catherine Collins, she is from Hungary, as you know, and Röst is a chief science advisor to Hungary government for the pandemic. Although his hobby is mathematics, linear differential equations, butterfly equations. So I'm very happy Gege is here and has spent his career process cruised with the Fields Institute to Toronto and benefit a lot from our distinguished colleague work with in many different ways. So I'm very happy Gege is with us today and he's going to talk about butterfly equations.
Thank you very much. Thanks a lot for that. I think it's on now.
Yes.
Yeah, but now I cannot use the pointer anymore.
Just move your mouse over to the computer. Your mouse is on the wrong screen.
Move the mouse all the way to the right.
Yeah. Oh, you moved it back. Move it over.
The mouse all the way to the right.
Yeah, I should remove the slide.
No. No, it's okay. And I cannot go back and forth. So
So
sometimes.
you have to go back on this,
Okay.
and then this is how you move forward.
Yeah. It's, again.
So every time I press it, it works. There.
Okay.
Just do it like not in the middle, and to the side. Perhaps. Yes.
Come back.
Yeah.
And pointer.
Pointer is this. Yeah.
Super. Okay. Okay. So sorry about this technical things at the beginning. Yeah. So we'll talk about blowfly equations. So let's start with what is a animal that mathematicians most interested in. So I did some very basic statistics from the publication database. So first guess is a dolphin, very popular animals. There are only very few papers about dolphins, and mathematical papers. So let's look at elephants, also popular animal. A bit more papers about elephants, but still not too many in the MathScience database. So about dogs, actually this is our family dog in the picture, a bit more than elephants. So what about mosquitoes? Not very popular, yes, but many papers in mathematics about mosquitoes, also at the workshop, partly because it's a vector for many infectious diseases. So people write about modeling mosquitoes and mosquito-borne diseases. But there is another one with a similar number of papers, and this is the blowfly. So the question is why there are so many papers about blowflies. It's not, doesn't seem to be so important or so central in ecology or for our life. Why there are so many papers about blowfly equation or blowflies. So to understand this, we go back a little bit in time and start with this very classical paper, 1948, by ecologist Hutchinson. I'll go back if I can. Okay. So circular causal systems in ecology. And at one part of the paper, Hutchinson introduced the time delay into the classical logistic equation there. Yes, so you can see. And the reason for that to explain some oscillations observed in ecology. And it was well understood in the paper that introducing a time lag can create oscillations as opposed to the classical logistic equation when solutions converge to the carrying capacity. If you put in the time delay, then solutions can go above the carrying capacity for a period of time, overshoot, and then come down and repeat. And in a footnote, it was also discovered already at that time that there is a critical value of the delay, pi/2, which we all know very well comes from this characteristic equation about the linearization of this equation at 0, so that the critical time delay was already calculated or mentioned. It was calculated in the footnote, so that oscillations are sustained for delays larger than this pi/2. So two other parts of the papers, there are some explanations why exactly the time delay was introduced. One is about Daphnia populations when oscillations were observed already, and they mentioned the fact that the fertility of a Daphnia female is determined not only by the current population density at a given time, but also by past densities to which it has been exposed. And they also suggest that time lag can contributing factor in generating cyclic changes in populations of mice. So, and then a few years later came the experiments of Nicholson in Australia about the Australian blowfly population. So this is the blowfly species, and this is the damage it can cause into the wool of the sheep. So it's concerned, Australian sheep farmers were concerned about the blowfly, the damage by the blowfly. Anyway, Nicholson did a series, many years, laboratory experiments, counting the population of blowflies and the different circumstances in cages. They found this interesting dynamics that you can see the cyclic behavior, oscillations with very large peaks, and then population drops to very low levels and then repeat. So then, of course, it was very tempting to try to explain this with the delayed logistic equation, which was known already at the time, and that's what Robert May attempted. So in this work, he fitted the data of Nicholson, he fitted the delayed logistic equation to the data of Nicholson and found a reasonably good fit. However, there were some issues with that, which were highlighted in this paper, Nicholson's Blowflies Revisited, published in Nature in 1980, when the authors had the following issues: that the time delay in May's fitting was not corresponding to any, that didn't have a biological meaning. It was not the same value that you would expect from maturation delay from other biological component of the blowfly population. And second, the delayed logistic equation will never produce solutions which has double peaks. And it was very well seen in the Nicholson, the blowfly data. You can see double peaks almost everywhere. So with the delayed logistic, you cannot produce that. So instead they produced another equation, which we now call Nicholson's blowfly equation. It's a simple scalar delay differential equation with one nonlinearity, this function x to e to minus x shape. You can see like this for the burst function with the maturation delay tau. And with this, we can produce solutions like this, resembling the original blowfly data. So similar equations have been proposed even earlier with you have a mortality rate, mortality term, and you have production and reproduction function with some time delay. So this equation now fits very well into the standard theory of delay differential equations. So we can formulate dynamical system in a space of continuous functions. And of course, the state of the system is always the segment of the solution of length tau. Tau is the delay. So you can imagine we're looking at solutions, and along solutions, the current state of the system is always this, what we see in this time window, and that determines future evolution of the system. So there is the standard theory for that. What is also useful in this context is to the positivity of solutions. So we're looking at the cone of non-negative functions. From population model, we're interested in non-negative populations. And a very common tool is used here is the monotone semiflows. But unfortunately, the blowfly equation is not monotone, just a monotone semiflow in general, but in some special cases, we can still use monotone semiflow theory. So they are the three basic mathematical situations what we can have. Here, the red line is the mortality, so mu times mortality rate of the population. And here we have the reproduction function. And if mortality is very large, then we have only one, because intersection of this curve with this line would give you are the steady states. So when it intersects only at 0, so mortality is very large, it's easy to see that 0 is globally attractive. So all positive solutions go to 0, population dies out. Next situation is when we have a positive steady state, but in the increasing part of this function, then this is stable for all values of the delay, locally and also globally. So all solutions then converge to this steady state. The most interesting situation mathematically is when the steady state is in the part when this reproduction function already decreasing. So, and we can easily characterize these three situations. And in this case, as you will see, the interesting dynamics can happen. So if we look at the stability of the positive steady state, again, we can separate in the parameter plane to two parts. The upper part is when we always have stability for all values of the delay, and the lower part is if we increase the delay, then we move in this parameter plane along lines. So, and we cross this, whenever we cross these curves, pair of eigenvalues on the complex plane move to the right. And then we have loss of stability when we cross the first curve here. So then we can have delay-induced instability. So in this case, what happens in this case? So we know when a cross of eigenvalues crossing the imaginary line, we can have a Hopf bifurcation. So I jumped too much. So of course, the bifurcation can be supercritical or subcritical. And in one case, we have a stable limit cycle on one side of the critical parameter, and in which case was the delay. Or if it's subcritical, then we have an unstable periodic orbit on the other side of the bifurcation point. So it's very important to distinguish between the two cases, which is usually much more difficult than just simply detecting there is a Hopf bifurcation, but we can see from the study the characteristic equation. So for delay differential equations, of course, the phase space is infinite dimensional, but still there's a well-developed theory. I don't know why I jump so much always. There's a well-developed theory for bifurcations, and actually how to calculate the direction of the bifurcation for nonlinear delay differential equations was already in this chapter in this book of Hazard, Kazarinov, and Wan. And there is also, like I mentioned, the book of Zhang Hong about the theory, bifurcation theory for functional differential equations. So there are different approaches. What we used in our calculations was the one from this paper, Faria and Magayesh, normal form approach. So going back to the Hopf bifurcation for, I cannot jump just one step. Anyway, so there's this paper of also Michael Lee from 2005 studying the Hopf bifurcation for blowfly equation, both local and global, but here I consider only the local version. So, and they have this theorem that we have this large formula here, sometimes also called first Lyapunov coefficient. And here in the formula, there are some of them are model parameters, A n star, tau 0 is critical delay, omega 0 is imaginary part of the critical eigenvalue, and so on. So there is a big formula, and the theorem says, depending on the sign of this formula or this large expression, if it's negative or positive, there is a supercritical or a subcritical Hopf bifurcation. So what we did recently is we could simplify this large formula and actually, yes. So actually we pointed out in a recent paper, István Balázs, that there is always a supercritical Hopf bifurcation, cannot be subcritical. So that formula before, it always has the same sign. And it is true not only for the first bifurcation, so it was in the, you can see that it was in tau 0 and omega 0, so the first values at the first bifurcation point, but it is true for any k, any further bifurcations, any subsequent bifurcations, for all parameter combinations for the blowfly equation, always supercritical. And actually it's more or less straightforward calculations, but quite long calculations. You can find this, which were published recently. Yes, all the subsequent ones also. And for all parameter values, whenever we have the bifurcations, it's always supercritical. Yes. Sorry?
Where?
It's this paper, International Journal of Bifurcation and Chaos. Actually, it's a relatively short paper, I think 6 pages. So eventually it reduces to the sign of this after some manipulations and calculations. So that was about the local properties of the steady state, but there are, of course, many people who were interested in global stability as well. So there are some well-known results. For example, 1991, positive equilibrium is always globally asymptotically stable when we have this relation, which basically means when this is the same condition for delay-independent stability, so also called absolute stability. So this absolute stability implies global stability, but there are also delay-dependent global stability results. And there's also when we don't have global stability, we're still interested in where the solutions can go, and at least we try to locate them. So this is also from an old paper, actually, these results when we had these numbers, alpha, beta, we can define also geometrically this way. And the global attractor is always inside this interval. So solutions eventually go between these values. We can even make it sharper for smaller, located to even smaller interval. I don't go into details here, but just show maybe this picture that we have delay independent estimates for global attractor are these dashed lines, and we have the delay dependent sharper estimates for the straight solid lines. And of course, we also shown that if you increase the delay, then of course the delay independent estimates of the change, and for very long delay they approach the delay independent estimate. So in that sense, delay independent one is sharp. And we can also look at the phase space about the structure of the solutions, and we can show there is a heteroclinic connection from zero, positive solution starting from zero, heteroclinic solution connecting to either the positive steady state or periodic orbit around that steady state. And I mentioned one, it is not our paper, it's a paper of Zhao Hong with his colleagues. A correction to this biologically reasonable correction to the blowfly equation is that adding this term, this e to the minus delta tau term in front of the reproduction function. So this represents mortality in the before maturation. So because mathematically we can manipulate the delay and look at the time delay as a parameter, but of course, longer the time delay biologically, if we have mortality before maturation, a smaller fraction of the population will survive the maturation period, and that is reflected in this term. And if the delay will become very large, then of course population will die out because many of them will die before maturation. So, and then this bifurcation picture is slightly different with this correction term. I just took one picture from this paper. So then these branches, that these bifurcation points, then we have just finitely many because of very large delays. We don't even have the positive steady state anymore. And these finitely many bifurcation points are connected by branches like this. So, and there are many more generalizations. I just mentioned this, already this Nature paper had more than 400 citations up to date, and then many papers dealing with this equation, not even citing that. So maybe 1,000, 2,000 papers roughly can be out there about the blowfly equation. And of course, a lot of variants people try to apply to other species, make it non-autonomous with multiple delays, make it looking at blowfly dynamics in space. And I just mentioned some researchers who did a lot of work in these directions. There's Zafaria, Chinfuzo, and Elena Braverman, but also many others. So here I will show you three extensions or has some biological motivation. One is what happens if we have heterogeneity in maturation sites. So the eggs, the blowflies lay their eggs at different locations, and some are better than others. And another one is joint work with Qingfu. He's very patient. I'm so slow with this for many years. He's waiting for me, but I hope this will come to an end now very soon. And third one is a joint work with Stephen Gergely, who tragically died not so long ago, and Rongstong Liu, when we introduced competition during the maturation period. So with the heterogeneity, you just simply consider, in the simplest case, just two sites, and the blowfly, with some fraction, they lay their eggs in site one, and some other fraction of them, the remaining fraction of them, lay their eggs at site two. And then we have a slightly different equation, and then the adults, they can fly over. So regardless of when the egg was, the adults afterwards can fly around and lay their eggs at the other site as well. So they mixed in space as adults. Of course, the eggs don't move. So we have a slightly different equation now with some additional parameters corresponding to what fraction of eggs go to site one and what are the circumstances at site one, which can be mortality rate during maturation period and also maturation delay. And so there is what we might expect is that distributing the delays now, so two sites might have different maturation periods, can make the system more stable. So to have a good comparison with this blowfly equation, of course, we have to match the parameters so that the average delay in this upper equation will be the same as the delay here, and the average survival fraction of population in the two-site model is the same as in the first one-site model. And we have some partial results that it's more stable, not generally proven yet, but there is one example of one parameter configuration when the heterogeneous model is stable and the homogeneous one oscillates, with these parameters being the same. So another interesting question is what we have now: two different species, two different strains of the same species competing with each other, and they have different maturation periods, which is the joint work with Xingfu. So now we have a system of two equations corresponding to the population sizes of the two species, and the competition is the BB is the birth function, which is the per capita birth rate, to be more precise. So the competition between the two species is expressed by these beta and alpha parameters. So when beta is larger, then UT, the second species, has a more detrimental effect on the first one, and vice versa with alpha. So, and then we can look at this reproduction number of the species 1 and 2. And of course, we can write the steady state equations, and we can distinguish basically two different cases. One is what we call weak competition, when this term reflecting the strength of competition are smaller in this combination alpha beta, or strong competition when they are larger. And then these are configurations of the steady states. So they have just the trivial steady state, or just one species present, or the other species present only, and coexisting steady states. And here, this is outside of this triangle, while in this case, it is inside, and we have dynamical differences as well. So basically, what we could see characterizing the dynamics, we use the assumption that when only one species is there, then it's a globally asymptotically, goes to a globally asymptotically stable state. So basically, we could divide the R1, R2 parameter domain into these regions when we have extinction of both species, or one equilibrium is globally stable, or the one boundary equilibrium, or the other one, or we have one stable, the other repeller, or we can have both repellers. So that the major difference between the two cases, the weak and strong competition, is corresponds to region 4. Also, the shapes are different, but in region 4, both boundary steady states are stable, and in this one, they both are repellers. So if we introduce a trade-off, so you can think shorter maturation period is always better because they start to reproduce earlier. But of course, it comes with a price, like everything in evolution. So you can also think that if there is a shorter maturation period, then when the individuals in the species reach the reproductive age, they start to reproduce. At that time, they are weaker, corresponding as opposed to they would have more time to mature. So this is reflected in this trade-off function. So longer delay. So this is the relation between the delay and the reproductive success. So, and with this functional form, we can actually create this invisibility plot. So showing that when a mutation, so imagine there is one species present with a particular maturation delay, and another species with another maturation delay, which can be emerging from a mutation or something, can invade the species or not. This is in this plot. So, and from this plot, we can see that there is a particular, with this functional for trade-off function, we have a particular maturation time, which is globally evolutionary stable and convergent stable strategy. So species will settle at this maturation time. So this uses the assumption that in the absence of the other species, they always settle at a steady state. But it's a very interesting question, I think, and it's challenging if there is an oscillatory population is it easier to invade it or it is more difficult to invade it? So it is useful for a population in that sense to follow oscillatory dynamics. It is more protected from invasion or not. So I just very briefly talk about the other larva competition. So in this paper of Stephen Gorley and Rongsong Liu, they used, by means of a structure, a model during the maturation period. So A is age between 0 and tau. Tau is the end of maturation period, when the individuals, they not only have a natural mortality rate, but they also have intraspecific competition represented by this term. And then they arrived at integrating these along characteristic curves. They derived another form of Blowfly equation that also has this mechanism of larval competition, and it is in this form. So one way to make this model more realistic is because here competition is only between larvae of the same age, and not an older larva does not compete with the younger larva in this formulation. So if you want to include that, of course, then we need a more complicated model with the integral term with this kernel function. This kernel tells us the level of competition between larvae of age A and A bar. And basically what we found roughly is that, so these are, the dashed curves are what would be the reproduction in the absence of competition, and the solid curves is with the competition. And in some cases, there's just a minor modification. But in other cases, when the within-host competition is stronger, this can lead to this function with a different shape with two peaks, or it can even generate more steady states. So larval competition can generate more steady states and more complicated dynamics consecutively, and also very strong larval competition can lead to the positive steady state becoming very small. So there are also several open questions, even for the classical form of the Blowfly equation. Here I mentioned some. So there is the delay-dependent stability results. So this still goes back now almost 20 years, and they found this. So this is again in a parameter plane. These are kind of combined parameters for the Blowfly equation, and this is the one of these curves is the local stability curve. Another one is a global stability curve for the Blowfly equations, and we can see a very tiny gap between the two, which means local stability implying global stability is still not solved for the Blowfly equation. There is this small gap. There's other kind of problems is the existence of 4 periodic orbits, which for global bifurcation results, they should be excluded. And there are some results, but they all come with some conditions on the parameters. Here is a square root 2, and here is this sigma is about 1.16. So can we go beyond that? Is it more general, the non-existence of 4 periodic solutions? And yeah, what is the structure, global structure, when we beyond further bifurcation points? So, and now I go back at the end of the talk, I go back to this equation, Hutchinson equation, where we started the talk. And there is another form, a mathematically equivalent form of the delayed logistic equation. And this was proposed by Wright in 1955, not from biological considerations, but from completely different mathematical interest about the distribution of prime numbers originally. But it led to by simple change in variables, this is the same equation as the delayed logistic equation. And he had several papers about the dynamics of this equation. And one of the most famous conjectures in delay differential equations were the Wright conjecture, which saying that this pi over 2 is not only a threshold for local stability, but also when this alpha smaller than pi over 2, then we have global stability. And from this conjecture from 1955 was solved in 2017 by Vandenberg and Jacquet, building on earlier results from my colleagues in Szeged. And basically the proof uses a combination of analytical tools with reliable numerical tools. It's also computer-assisted proof using reliable numerical calculations. So going back to the bifurcation of this equation and in a slightly more general form of equations, I will call them right type equation, just scalar equation with a single delay. And the delay is now normalized to 1. You can scale it by times rescaling. We can always put it into the parameter in front of the nonlinearity. And we can also normalize, the nonlinearity by mu in a way that in the Taylor expansion, the first coefficient is always 1. So we know that the direction of the bifurcation depends only up to terms of order 3. So we have just 2 free parameters now in F, and we have the bifurcation parameter mu. So this is just the expansion of F. So, and then again, by the approach of Faria-Magalhaes, we could characterize all possible bifurcations in a simple form. Basically, in this theorem, that we have this function h of k expression for the case bifurcation point. We have the bifurcation is supercritical if this relation holds and subcritical if the opposite relation holds. And C and B are these coefficients just here. So this is a very easily checkable, trivial to check this condition for any nonlinearity and for any bifurcation point. And we can visualize it in this figure. This is h of k. So you have to look only at integer points, of course, for the case bifurcation. So, and basically it says that you just have to look at C over B square, and that tells you everything for direction of all bifurcation points. If C over B square is below this one, then all bifurcations supercritical. If it's above that one, that dashed line, then all bifurcations subcritical. If it's in between, then it depends on K. Whenever it's below this, the blue dots, supercritical. So actually this one, well, for K equals 0, this also calculated in the book of Hal-Smith, but it's with the different, by extending, we can extend it to not just the first bifurcation, but to any. So I'm just showing that the calculation is just this long. So it's fairly simple. And we used again the Faria-Magalhaes method. And this way, why jump so much? Yes, I'm very poor with this button. So yeah, so some examples. This immediately gives the well-known results for Wright's equation, all half bifurcation supercritical, also for Ikeda equation, another well-known equation with single delay. But we can construct examples also, which is totally subcritical, so all bifurcations subcritical, or we can also define cubic equations when we have a switch. Some bifurcations are subcritical, but then it switched to supercritical for later ones. And actually all possible configurations we can show for the sequences of sub or supercritical bifurcations. So we know that some particular sequences are not possible. So this is a complete characterization. So we cannot construct a nonlinearity such that, say, you have 3 supercritical bifurcations and 2 subcritical and then some supercriticals again. That's not possible. Let's skip this. So finally, I'd like to show how we can relate bifurcation results to some more global problems for Wright's equation. So, and then we will consider this so-called Cook transformation, which actually consider a periodic solution with period capital T. And this is a simple observation that then Q of T, when L is some integer, a positive integer, is also a periodic solution. And first you can check it's also a solution of the equation, and it's also periodic, but with a different period and with a different parameter in front of the nonlinearity. So by this transformation of a periodic solution, you can find another one with a different parameter and different period. So then you can define this mapping, Cook mapping, which for a given integer maps periodic solutions to other ones. And actually, it's easy to see that this mapping that maps local bifurcation branches onto each other. So you have a local bifurcation branch, Cook transform will give you another one corresponding to another bifurcation point. Depending on this integer, you can go whenever you want. So another thing is the Cook transformation also makes a connection between the parameter and the period. So when you know something about the period locally, then you can know something about the solutions for different parameter values and vice versa. So this way, we can find local estimates for the period functions, for example, if we know the directions of the bifurcations. Because, for example, from a supercritical branch mapped onto another supercritical branch, that we know that the new parameter after Cook transformation should be on the right of the critical parameter. But the period also included in the parameter. So then we have information about the period itself. So we can have, for some cases, lower, some cases upper estimates locally about the periods of the periodic orbits on the branches. And this is an example here. These are our estimates, and the blue is a numerical calculation of the periods. And we can do it the other way around. So when, imagine you know something about the period function, then that gives information on the direction of some bifurcations. So we can use it for the following. So there was another famous conjecture, which is now proven, Jones conjecture, which says that for large parameters larger than pi/2, there is a unique slowly oscillating periodic solution for the Wright's equation, which is now in this can be transformed equivalent to this single delayed form. So, and in the paper, when it was proven, there was a new conjecture which showed that the period length of slowly oscillating periodic solutions increases monotonically in the parameter. So by this monotonicity was shown for a small interval. But by this Cook transform, we can actually extend it to other branches. So we know that for later branches with more rapidly periodic solutions, more rapidly oscillating periodic solutions, we also have intervals when the period increasing monotonically. And we can also exclude now with the Cook transform isolas. Isolas are these structures in the global bifurcation diagram when periodic orbits just appear. So it was excluded for the slowly oscillating periodic solutions by the proof of the Jones conjecture. Now it's also excluded for the branches of for rapidly oscillating periodic solutions. We could also exclude isolas. What is not excluded yet is the folds in the branches of the rapidly oscillating and at the later bifurcation points. So summarizing, so for this, we have this decisively simple looking scalar nonlinear delay differential equations. And after many decades of research and lots of results, there are still many questions about them. We used many sophisticated toolbox from mathematics. And these results are presented. And then these are my related papers over a period of 15 years. And now to finish my talk, I will say something very off topic of the talk, but not off topic of the meeting. So we had, in the pandemic, we had COVID-19 Modeling and Epidemiology Task Force, which I was leading in Hungary, which was major scientific advisory body in this time period from 2020 March to 2022 March. So we had many very close contact with the government, with weekly briefings and so on. It was a multidisciplinary group, very multidisciplinary, with epidemiologists, medical doctors, public health, mathematics. Even we had very good computational social scientists. So this task force is finished in 2022 March, and it was quite successful. I just show one letter I like to show from European Director of WHO, acknowledging the Hungarian approach in mathematical modeling of the pandemic. So now government, why am I out of the slideshow? So anyway, it was the last slide, now it's back. Yeah, so now we have new institution in Hungary based on the task force, the National Laboratory for Health Security, which is now much larger than the task force was, with a much wider scope. So not only COVID, but all kind of health security issues, infectious diseases and ecological monitoring and so on. So it's a very large national laboratory, and we got significant funding for the next 4 years. And there were some other initiatives in the United States. US CDC has a new institution, outbreak analysis, I don't know what the name, National Center for Outbreak Analysis. The WHO has a new hub in Berlin of epidemic intelligence. So this fits into this trend to create these centers. But I think what's special is that the very heart of this, there is mathematics here. And we have got good funding for the next 4 years. And I think that's why I'm telling you this. It's a great opportunities for further Hungary-Canada collaborations in this field of research. So you're all mostly welcome. We can host postdoc researchers from Canada, or more senior researchers for shorter research periods, or all forms of collaborations. I'd be very happy to have. So thank you very much for your attention.
Will be invited to be located in Hungary.